Class 250 degrees Celsius insulated cables are designed to operate at temperatures up to 250 degrees Celsius with a maximum conductor temperature of 250 degrees Celsius. Article 310 of the National Electrical Code applies to all wiring installations. The ampacity specified in Table 310.16 for 75 degrees Celsius conductors are applicable when the ambient temperature does not exceed 30 degrees Celsius, which is equivalent to 86 degrees Fahrenheit. To determine the appropriate ampacity for temperatures exceeding 30 degrees Celsius, refer to the adjustment factors provided in Table 310.16. For conductors with a 250 degrees Celsius insulation rating, the ambient temperature is limited to 250 degrees Celsius, which translates to 482 degrees Fahrenheit. An ambient temperature of 600 degrees Fahrenheit or 316 degrees Celsius exceeds this limit and therefore cannot be used with 250 degrees Celsius rated conductors. A 250 degrees Celsius insulated conductor is not suitable for use in an ambient temperature of 600 degrees Fahrenheit. When working with electrical wiring, it is crucial to understand the temperature ratings of the conductors and their insulation. The temperature rating indicates the maximum temperature at which the conductor can safely operate without degrading its insulation or affecting its performance. Exceeding this temperature can lead to insulation breakdown, short circuits, and even fire hazards. TGGT wire is a type of high-temperature wire commonly used in applications where conductors are exposed to elevated temperatures, such as in industrial ovens, heating equipment, and other similar environments. The TGGT designation refers to the specific insulation materials used in the wire's construction. The temperature rating of TGGT wire is typically 250 degrees Celsius, meaning it can withstand continuous operating temperatures up to this level. However, it is essential to consider both the conductor temperature and the ambient temperature when determining the suitability of TGGT wire for a particular application. The conductor temperature is the temperature of the wire itself due to the current flowing through it. The ambient temperature is the temperature of the surrounding environment where the wire is installed. The National Electrical Code, or NEC, provides guidelines for the safe installation and operation of electrical wiring systems. Article 310 of the NEC addresses conductor ampacity, which is the maximum current a conductor can carry continuously under specified conditions without exceeding its temperature rating. Table 310.16 in the NEC provides ampacity values for various conductor sizes and insulation types, based on an ambient temperature of 30 degrees Celsius. However, in situations where the ambient temperature exceeds 30 degrees Celsius, the ampacity of the conductor must be adjusted using the correction factors provided in Table 310.16. These correction factors account for the reduced heat dissipation capability of the conductor and higher ambient temperatures. To determine the appropriate ampacity for a conductor in a high-temperature environment, firstly, identify the conductor size and insulation type. Secondly, determine the ambient temperature in the area where the conductor will be installed. Thirdly, consult Table 310.16 in the NEC to find the ampacity of the conductor at 30 degrees Celsius. Fourthly, refer to the correction factors in Table 310.16 to determine the appropriate adjustment factor for the ambient temperature. Fifthly, multiply the ampacity at 30 degrees Celsius by the adjustment factor to obtain the adjusted ampacity for the high-temperature environment. It is crucial to select a conductor with an ampacity that is sufficient to carry the intended load current, taking into account the ambient temperature and any other relevant factors. Using a conductor with an inadequate ampacity can lead to overheating, insulation damage, and potential safety hazards. In the case of an industrial oven with zone temperatures reaching 890 degrees Fahrenheit, it is highly unlikely that TGGT wire with a 250 degrees Celsius temperature rating would be suitable. The ambient temperature in some parts of the oven could be as high as 600 degrees Fahrenheit, which exceeds the maximum operating temperature of the TGGT wire's insulation. In such a scenario, using TGGT wire would pose a significant risk of insulation failure and electrical hazards. Alternative wiring solutions should be considered for high-temperature applications exceeding the limitations of TGGT wire. These solutions may include using conductors with high temperature ratings, such as mineral-insulated cable, or employing specialized wiring methods that provide additional protection against heat. Mineral-insulated cable, or MI cable, is a type of cable that consists of copper conductors insulated with a mineral compound, such as magnesium oxide, and enclosed in a seamless copper or stainless steel sheath. MI cable is known for its excellent high-temperature performance and resistance to fire, moisture, and corrosion. It is commonly used in demanding industrial applications where reliability and safety are paramount. When selecting wiring for high-temperature environments, it is essential to consult with qualified electrical engineers and adhere to all applicable codes and standards. A thorough evaluation of the operating conditions, including temperature, voltage, current, and environmental factors, should be conducted to determine the most appropriate wiring solution. Regular inspections and maintenance of electrical wiring systems in high-temperature environments are also crucial to ensure continued safe and reliable operation. This includes checking for signs of insulation damage, overheating, and corrosion, and promptly addressing any issues that are identified. In summary, TGGT wire is a type of high-temperature wire suitable for applications with temperatures up to 250 degrees Celsius. However, it is essential to consider both the conductor temperature and the ambient temperature when determining the suitability of TGGT wire for a particular application. The National Electrical Code provides guidelines for ampacity adjustments in high-temperature environments. In situations where the ambient temperature exceeds the temperature rating of the wire, alternative wiring solutions with high temperature ratings should be considered. Always consult with qualified electrical professionals and adhere to all applicable codes and standards when working with electrical wiring in high-temperature environments. Proper selection, installation, and maintenance of wiring systems are crucial to ensure safety and reliability. To further elaborate on the selection of appropriate wiring for high-temperature environments, several key factors must be carefully considered. Firstly, the maximum ambient temperature to which the wiring will be exposed must be accurately determined. This temperature should include any potential temperature spikes or fluctuations that may occur during normal operation. Secondly, the continuous current carrying capacity, or ampacity, of the wiring must be sufficient to handle the load current without exceeding the conductor's temperature rating. This requires calculating the load current and applying any necessary dating factors for ambient temperature and other conditions. Thirdly, the insulation material of the wiring must be compatible with the operating temperature and any potential chemical or environmental exposures. Different insulation materials have different temperature ratings and resistance to various chemicals and environmental factors. Fourthly, the wiring method must be appropriate for the application and provide adequate protection against physical damage, moisture, and other potential hazards. Common wiring methods for high-temperature environments include conduit, cable tray, and direct burial. Fifthly, all wiring and components must comply with applicable codes and standards, such as the National Electrical Code and relevant industry standards. This ensures that the wiring system is designed and installed safely and reliably. In addition to these factors, it is also important to consider the long-term reliability and maintenance requirements of the wiring system. High-temperature environments can accelerate the degradation of wiring components, so it is essential to select materials and designs that are durable and resistant to aging. Regular inspections and maintenance should be performed to identify and address any potential problems before they lead to failures or safety hazards. When selecting wiring for industrial ovens or other high-temperature equipment, it is often necessary to use specialized wiring products that are specifically designed for these applications. These products may include mineral-insulated cable, high-temperature silicone rubber insulated wire, and other specialized wiring solutions. Mineral-insulated cable is particularly well suited for high-temperature environments due to its excellent heat resistance, fire resistance, and mechanical strength. It consists of copper conductors insulated with a mineral compound, such as magnesium oxide, and enclosed in a seamless copper or stainless steel sheath. This construction provides exceptional protection against heat, moisture, and physical damage. High-temperature silicone rubber insulated wire is another option for high-temperature applications. Silicone rubber is a flexible and heat-resistant material that can withstand continuous operating temperatures up to 200 degrees Celsius or higher. Silicone rubber insulated wire is commonly used in ovens, furnaces, and other heating equipment. In some cases, it may be necessary to use a combination of different wiring products to achieve the desired performance and reliability. For example, mineral insulated cable may be used for the main power feeders, while high-temperature silicone rubber insulated wire may be used for the internal wiring of the equipment. Regardless of the specific wiring products used, it is essential to follow the manufacturer's instructions and all applicable codes and standards during installation. Proper installation techniques are crucial to ensure the safety and reliability of the wiring system. This includes using appropriate connectors, spores, and other hardware, and ensuring that all connections are tight and secure. In addition to selecting the right wiring products and installing them properly, it is also important to implement a comprehensive maintenance program to keep the wiring system in good condition. This program should include regular inspections, testing, and cleaning, as well as prompt repair or replacement of any damaged or worn components. Regular inspection should include visual examination of the wiring for signs of damage, such as cracks, cuts, or discoloration. Testing should include insulation resistance testing to check for deterioration of the insulation material. Cleaning should include removal of any dust, dirt, or other contaminants that could contribute to overheating or corrosion. By following these guidelines and implementing a comprehensive wiring management program, it is possible to ensure the safe and reliable operation of electrical equipment in high-temperature environments. Always consult with qualified electrical professionals for assistance with selecting, installing, and maintaining wiring systems in these demanding applications. To further expand upon the topic of dirty conductors in high-temperature environments, it is important to understand the underlying principles that govern conductor ampacity. The ampacity of a conductor is determined by its ability to dissipate heat without exceeding its temperature rating. When a conductor carries current, it generates heat due to the resistance of the conductor material. This heat must be dissipated into the surrounding environment to prevent the conductor from overheating. The rate at which heat can be dissipated depends on several factors, including the size and material of the conductor, the type of insulation, the ambient temperature, and the presence of other heat sources. When the ambient temperature is high, the conductor's ability to dissipate heat is reduced. This is because the temperature difference between the conductor and the surrounding environment is smaller, which reduces the rate of heat transfer. As a result, the conductor's ampacity must be reduced to prevent it from exceeding its temperature rating. The NEC provides rating factors for various ambient temperatures and conductor insulation types. These rating factors are applied to the ampacity values listed in Table 310.16 to determine the adjusted ampacity for the specific operating conditions. To use the rating factors correctly, it is important to accurately determine the ambient temperature in the area where the conductor will be installed. This may require taking measurements at different locations and times of day to account for variations in temperature. It is also important to consider any other heat sources that may affect the conductor's temperature, such as adjacent equipment or sunlight. In addition to ambient temperature, the number of conductors bundled together in a raceway or cable also affects the conductor's ampacity. When multiple conductors are bundled together, they share the same heat dissipation path, which reduces their individual ampacities. The NEC provides adjustment factors for the number of conductors in a raceway or cable. These adjustment factors are applied to the ampacity values listed in Table 310.16 to determine the adjusted ampacity for the specific number of conductors. It is important to note that the rating factors for ambient temperature and the adjustment factors for the number of conductors are cumulative. This means that if a conductor is subject to both high ambient temperature and multiple conductors in a raceway, both rating factors must be applied to determine the final ampacity. In some cases, the dirting factors and adjustment factors may result in a significant reduction in the conductor's ampacity. This may require using a larger conductor size to ensure that the conductor can carry the intended load current without exceeding its temperature rating. It is also important to consider the voltage drop in the conductor when selecting the conductor size. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for limiting voltage drop in electrical circuits. To minimize voltage drop, it may be necessary to use a larger conductor size or to shorten the length of the conductor. In addition to dirting conductors for high temperature and multiple conductors, it is also important to consider other factors that may affect the conductor's ampacity, such as the type of load being served in the operating cycle of the equipment. Some loads, such as motors, draw a high inrush current when they are started. This inrush current can cause the conductor to overheat if it is not properly sized. The NEC provides guidelines for sizing conductors for motor loads. The operating cycle of the equipment can also affect the conductor's ampacity. If the equipment operates continuously, the conductor will be subjected to a constant load current. However, if the equipment operates intermittently, the conductor will be subjected to a fluctuating load current. The NEC provides guidelines for sizing conductors for intermittent loads. By carefully considering all of these factors, it is possible to select conductors that are properly sized for the specific application and operating conditions. This will ensure the safe and reliable operation of the electrical system and prevent overheating, insulation damage, and other potential hazards. Always consult with qualified electrical professionals for assistance with selecting and dirting conductors for complex or critical applications.